Hello, my name is Caitlin Chapman, and this is my Lab 2 charge tape revisited. And so for a little bit of an introduction, we're just going to go over the purpose, the models, and fundamental principles that we used, in a brief preview of the main result. And so the purpose of this lab was to estimate the amount of charge necessary to float one tape above another by creating a model that represented a line of charges and which would calculate that electric force. And the fundamental principles that we used were Coulomb's law, the gravitational force, and Newton's third law. And after creating the model, we estimated that the amount of charge required to make the top tape float is about 1.28735 times 10 to the negative 6 coulombs, which is quite different from our Lab 1 result of 9.789 times 10 to the negative 9. Our initial conditions for the model, we had to isolate our system, which was the top tape, and the surroundings, which were the bottom tape and the earth. And both tapes in the model were represented by a line of red balls and a line of blue balls. And the mass of our tape was 0.22 kilograms. And the initial estimated charge, which is what we thought from our Lab 1, was 9.789 times 10 to the negative 9 coulombs. And then gravity constant is 9.8 meters per second squared. And so, getting started with our glow script, we needed to create a function that would calculate our electric field for us. And so that is what we're doing up top. We're taking the charge, and then we're going to create a variable for our location, which is going to have our observation point minus our source point. And then we put that into our field equation and return that. And then we have another function that's creating the line of charges for each piece of tape. And continuing on, this next section uses a nested for loop to calculate the force for each one. And as we go down that, we edited the line on line 120. That is the force on the top by the bottom, and right there we're just taking the charge of the top and multiplying it by the field at the top by the bottom, which was calculated in a few lines above. And then going down again, we edited on line 124 the field at the top arrow, which is just going to be the field at the top that we calculated earlier multiplied by the scale. And so that is what it looked like when we would run our code, and as you can see, the magnitude of the forces are pretty equal. We've got our line of point charges, and then we've got our field arrows, which are in green, and then our electric force is in the white arrow, and the gravitational force is on the yellow arrow. And both of those are acting on the top tape specifically. And so just looking at the numbers that we got from this lab versus our Lab 1, we can see that they're quite different. And we can also assume that the line charge model is probably more accurate because it uses smaller segments. And so yeah, that was the magnitude of our charge, was 1.287 times 10 to the negative 6. And what assumptions, approximations, or idealizations that we made. We ignored air resistance, and not necessarily in this lab, but the last lab we treated the tape as though it were a point charge concentrated in the center, but in this lab we treated it as though it were a line of charges. And we also assumed for both labs that each U-tape that we made were roughly the same amount of charge, evenly distributed. And some potential sources of error were the assumptions that we made. Our measurements weren't exactly 100% precise, and when handling the tapes, charge can be grounded in a way and get lost. And looking at our number, realistically, it looks quite high. Even though this model is supposed to be more accurate, I think something might be off with that, and it might be due to our gravitational force. But it just seems like kind of a high number for what we're looking for. But thank you.